Hello all, my name is Supunna Kandala. In this talk, I'm going to present to you our system Vista, an optimized system for declarative feature transfer from deep CNNs at scale. This is a joint work with my advisor, Professor Arun Kumar. If you look at the current state of enterprise data analytics, using most analytics pipelines are primarily powered by structured data. But in many of these applications, you also have access to large volumes of image data. These images contain important information about their respective domains, and as a result of not being used by their corresponding analytics pipelines, they have essentially become dark data from analytics point of view. Recent advancements in deep convolutional neural networks, CNNs, have tremendously improved our ability to automatically understand images. In the popular computer vision challenge ImageNet, models based on CNNs have achieved tremendous success, even surpassing human-level accuracy. And as a result, they now provide an opportunity to integrate image data with structured data for performing multimodal analytics. So what is a CNN? CNN is a special type of a neural network which makes the explicit assumption that the input is always going to be an image. Given an input image, it transforms it through a series of transformations organized into layers and finally outputs the probability for different class labels. Researchers have shown that when trained on image data, layers inside the CNN automatically learn to identify different features in the input images. Low-level layers automatically learn to identify low-level features like edge patterns and color blobs, and high-level layers automatically learn to identify high-level concepts. However, training a CNN is not an easy task. You need a lot of labeled training data in the order of millions, a lot of compute power in terms of a GPU cluster, and as a result, this process is highly time-consuming. Furthermore, you need to pick several configuration parameters during the training process called hyperparameters. And the chances are that if you're not an expert in training CNNs, you will find it very difficult to find a good set of training hyperparameters. Luckily, there's a paradigm called transfer learning, which can mitigate these limitations and still provide the benefits of CNNs. In the rest of my presentation, I'm going to first provide an example on how we can use transfer learning to integrate image data with structured data for performing multimodal analytics, then present our system Vista, an optimized system for executing this workload, and finally present some experimental results. So what is transfer learning? Let's assume that you are a data scientist working at an online e-commerce retailer, and you are tasked with developing a recommendation system to recommend products to your customers. For this task, so far, you have primarily used structured data, but you have a hunch that the product images also contain important information for this task. To incorporate product images, you take a pre-trained CNN, a CNN that has been trained on some other dataset like the ImageNet dataset, and feed the images through the CNN and extract the output of a certain layer as a representation of the images. You then combine it with your structured data to obtain a multimodal representation of your data, and then train and evaluate downstream machine learning models. But in a CNN, there are a lot of layers. Which layer you should extract? It turns out it's not possible to tell which layer will work best for your particular task. So you have to explore several different layers and pick the one that works best for your particular task. So how would you execute this kind of a workload today? Today, there is no one single system that you can use to execute this workload end-to-end. You have to use a deep learning system like TensorFlow, which is optimized for neural networks and provides seamless hardware acceleration to extract CNN features. But such systems do not provide features like performing ETL on your structured data, distributed memory and file management, and also support for classical machine learning models like random forest, which are provided by parallel data flow systems. So you have to export your CNN features into files and then load them along with the structured features into a parallel data flow systems and train and evaluate your downstream ML models. And repeat this process for all the layers that we're interested in exploring. This dichotomy between scalable systems for performing analytics today causes several issues for workloads that want to jointly analyze image data and structured data. First, there's a usability issue because now users have to manually manage CNN features by writing them into files. There's an efficiency issue because extracting one layer at a time causes a lot of redundant computations. To make it clear, assume that you want to explore layer 1, 2, and 3. The computations required to extract layer 1 is a strict subset of the computations required to extract layer 2 and layer 3. Also, there's a reliability issue because CNN layers are orders of magnitude larger than the highly compressed input images, which are in formats like JPEG. And as a result of this memory blow-up, it can cause costly dispills and also sometimes workload crashes. Next, I'm going to present you our system Vista, starting with an overview of Vista. Vista is a declarative system for scalable feature transfer from deep CNNs for multimodal analytics. It takes in 4 inputs: structured data, image data, pre-trained CNN and the layers interested in exploring, and the downstream machine learning model. Given these inputs, Vista optimizes the CNN feature transfer workload and reliably runs it. Now let's look into Vista's architecture. Vista has a declarative API which can be used by users to specify which layers they want to explore rather than how to stage the computations. It has an optimizer which performs automated logical, physical, and system configuration optimization. It comes with a roster of pre-trained CNNs where users can pick different CNNs from. It runs on existing parallel data flow systems and deep learning systems to exploit the orthogonal benefits of those systems. Here I have shown Apache Spark and TensorFlow, but techniques in Vista are directly applicable to other systems as well. Having a declarative API improves the usability of our system. Having an automated optimizer improves the efficiency and reliability, and also relying on existing parallel data flow and deep learning systems also improve efficiency, scalability, and fault tolerance. Now let's briefly look into what goes inside Vista's optimizer. In terms of logical plan optimizations, we identified this CNN feature transfer workload as a novel instance of the classical multi-query optimization in database management systems. If you treat extracting one layer of CNN features as a single query, exploring multiple layers essentially constitutes a multi-query. We evaluate several different materialization options. The current dominant practice of extracting one layer at a time can be categorized as the lazy approach. It has low memory footprint, but has high computational redundancy. Alternatively, you can extract all the layers in one go, which we call the eager plan, which has zero computational redundancy, but has high memory footprint. We propose a novel approach called stage, which takes into account the characteristics of CNNs and also the characteristics of this particular workload to provide the best of both worlds. By using stage, we can improve efficiency and reliability of this workload. In terms of physical plan optimizations, Vista picks the join operator between the structured features and the CNN features, and also the storage format for storing intermediate data in memory. For the join, the available options are broadcast versus shuffle, and they essentially trade off between memory footprint and network cost. For storage format, the available options are compressed versus uncompressed, and they essentially trade off between memory footprint and compute cost. Vista automatically picks these values based on the characteristics of the given workload. In terms of system configuration optimizations, one of the most important configuration optimizations that Vista does is memory allocation. When executing a workload that spans across both parallel data flow systems and deep learning systems, it turns out these systems have complex memory requirements. For example, parallel data flow systems need memory for query processing, UDF execution, and also storing intermediate data in memory. On the other hand, deep learning systems also have memory requirements for loading, storing, and performing inference on the CNN models. The default configurations that come with these systems often doesn't work, and as a result, they can cause dispills and even sometimes workload crashes. Vista frees the data scientists from these low-level manual memory configurations such that they can now focus on their ML-related exploration. Vista also picks the query execution parallelism. Increasing the query execution parallelism improves the system utilization, but it also increases the CNN inference memory because every execution thread will spawn its own copy of the CNN model, causing more pressure on the memory available for storing intermediate data in memory and causing dispills. Vista picks the core execution parallelism such that it improves both the system utilization and also reduce dispills. More details on how Vista optimizer navigates each trade-off space and finds the best option can be found in our paper. Now I'm going to present you some experimental results, and I will focus on a snapshot of experimental results due to time constraints. We used the Amazon product review dataset and selected around 200,000 records. Each record has 200 structured features, and the image is the image of each product. And the target is to predict whether each product will be popular or not. We used two pre-trained CNNs, AlexNet and VGG16, and explore last 4 layers and last 3 layers corresponding. As the downstream ML model, we use logistic regression. We evaluate several different approaches. Lazy is the current dominant practice of extracting one layer at a time. Eager corresponds to extracting all the layers in one go, and Vista is the optimizer pick plan. For Lazy, we also vary the query execution parallelism between 1, 5, and 7. For AlexNet, Lazy 1 took around 162 minutes to complete this workload. By increasing the query execution parallelism, this runtime can be reduced up to 45 minutes. Eager and Vista both takes around 16 minutes, giving us a 10x speedup. For VGG16, Lazy 1 took around 345 minutes to complete this. However, Lazy 5, Lazy 7, and Eager all crashed due to various memory-related misconfiguration issues. Vista completed this workload in 61 minutes without incurring any workload crashes. Experimental results for other data systems, datasets, and drill-down experiments can be found in our paper. In summary, I presented to you our system Vista, which is an optimized system for scalable deep CNN feature transfer for multimodal analytics. It performs DBM-inspired optimizations, and by doing so, it is able to improve the efficiency of this workload and also avoid unexpected workload crashes. As for future work, we plan to extend this kind of multi-query optimization techniques for other forms of deep neural network feature transfer and text data. More details about our system, including the system code, can be found in our project webpage. With that, I would like to conclude and take any questions if you have. Thank you.